Hello everyone. For this digital media, I will walk you through one of my past machine learning projects using Python, the Steam Game Recommender. Our task here is given the user and game pair, we're going to predict whether the user will play that game or not. This is very useful, as you can see from our current online marketplaces, where you can see a lot of predictions made based on your prior buying histories. So we'll first look at our dataset. This dataset is directly collected from Steam with 175,000 reviews, and it contains information like hours played by the user and a unique game and user ID that can uniquely identify the game and the user. So these IDs were passed through a hashing function so that they're anonymized to protect the user's privacy. In terms of raw data, that's basically all we have here. So we'll now see how we extract some kind of useful information from our data set. So the first step here is obviously training and test split to avoid overfitting our models. We've picked a validation set size of 10,000 and the rest of it is training set. Then we proceeded to build a quote unquote database for both the games and the users in our data set so that given the user, we can have a list of games that the user have bought and vice versa for if given a game, we can have a list of users that have bought that game. Right. So after we build this, we'll have a way of querying whether you have a user or a game. This is very useful in building our features. So we'll talk about that in the next section. So here we picked just a basic Python dictionary to do that, which is more than enough for our purposes. After that, we also built a user game played dictionary, which is a double map from a user to a game to a Boolean value. This is used to construct our training and validation labels so that we can verify if our own predictions are correct on the training set. However, there is kind of an obvious catch. Since we constructed this dictionary by looping through our own data sets, it's only going to have positive or true values. So as a result, it will be very, very unbalanced, basically 100% positive and 0% negative to train on any kind of machine learning model. So we solved this problem by using a negative sampling, which basically means that for each user and game pair in this user game played dictionary, we will randomly sample a game that the user haven't played. You might say, what about when you're randomly just sampled on a game that the user had played? We can see here that we did kind of a loop. So as long as you didn't encounter a game that the user haven't played, we'll skip over that and sample the next game. So for each user and game pair, we will eventually found a negative sample for that user and game pair. And we insert that into our dictionary so that we will have basically a perfectly balanced test and validation set. After we have a process data set, we need to build the features to train on machine learning models because most of the machine learning classifiers requires you to have some sort of numerical vectors as the training data. So we have three main ideas here, popularity, similarity, and Bayesian personalized rankings. We'll start with popularity, which is kind of the most important one. As it turns out, most of the game buying decisions on Steam are popularity based, which basically means that people are just more likely to buy a popular game. And this feature turned out to be really, really effective in our task. Here we chose a normalized popularity value, which basically means kind of a scaled version of the number of people that played that game. So basically, whenever we encounter a user and game pair, we will first check that the popularity, if that popularity exceeds certain threshold. If it does, the user then is more likely to buy the game. Secondly, we have similarity. It's a really simple and powerful tools for recommenders. As you can see, we only have 2 lines of codes here for similarity. Here we use both Jacquard and cosine similarity as a quantified measure for user similarity. So basically, given 2 sets of games that 2 users have individually bought, we calculate a measure of similarity score between those 2 users. The rationale here is that, well, people will buy games if that game is also bought by a similar user. This is the same type of recommendations you actually saw on Steam, where a recommendation is made based on whether your friends bought or whether a person similar to you have bought. Finally, we will have the most sort of complicated feature that we included, which is Bayesian personalized ranking, or BPR. For each user and game pair, it will calculate a probability of the user playing that game. It's based on sort of a similarity metrics, but also many other neural networks related features. So I will not go into the details, but if you're interested, I have linked the original paper for BPR on my projects page, so you can check that out. This BPR training program is built using TensorFlow Keras, and we will include the BPR score also as a feature into our final feature vectors. And finally, we have model selection. We did a 5-fold cross-validation using logistic regression, random forest classifier, decision tree classifier, and support vector machines. Eventually, as you can see here, the good old logistic regression prevailed with just about 71% accuracy on test set. This means that if we're given an unknown user and game pair, our recommender will have about 71% chance of making the right decisions on if the user will buy that game. If you think about it, that's pretty good. So yeah, that's basically it about my Steam game recommender. You can check out the source code of this project on my projects page, and you can feel free to contact me for any questions. Thank you.